concept of electric current, but today I'm also going to talk about batteries, and then I would like to give a demonstration about semiconductors. So I would like to first of all describe the conundrum from where we finished off the previous lecture, and I'm going to describe how our electric field is set up inside current carrying conductors. And we finished off our discussion on the fact that if we have a battery that is connected to a circuit, the dipolar field from the battery cannot explain the production of electric fields, because the electric fields don't turn out to be in the right directions, they don't turn out to be in the proper magnitudes. Hence, a steady current cannot flow through the circuit. Now, if we, the first example I would like to talk about is quite simple but very illuminating. Suppose I have a battery and I'm drawing a battery by its physical sketch. So the battery has two terminals. One of these terminals or plates has a preponderance or a large positive charge on it. It's a net positive charge, whereas the other terminal has a net negative charge. So this acts like a dipole. So it's a separation of charges. These charges have somehow been separated inside the battery. Now this battery is connected to a circuit, and I represent that circuit by a simple wire. This wire may have some resistance. So this is a simplistic representation of the circuit. Now in the circuit that I'm going to draw, I'm not going to close this circuit, rather there is a gap and there's air inside this gap. So these are just two wires that are protruding from the terminals of the battery. Now this has an infinite resistance, this gap has an infinite resistance, so this is my gap, which means current cannot flow through the circuit. But this wire is connected to the positive terminal, this end of the wire is connected to the negative terminal. So if a current cannot flow through the circuit, and once the wires have been connected and the equilibrium has been restored, there is no flow of charges inside the wire. And remember, by flow of charges, I mean the flow of the electron sea, that is the entire sea of electrons. By a current, I'm not referring to the thermal fast motion of electrons, rather I'm referring to the motion of the sea of electrons. Now if there's no current flowing through the circuit, would there be any electric field inside these wires? Ji. Why should there be an electric field? If there were an electric field, charges would flow. This is a condition of electrostatic equilibrium. So charges cannot flow. There is no current through the wire, so there cannot be an electric field. Q flow karega? Once equilibrium has been established, all the charges have been set up, the current cannot flow through the circuit, because if current flows through this wire and it has no path to go onwards, charge will just accumulate here till negative feedback occurs and the current ceases. So once equilibrium has been established, there can be no electric field inside this conductor. It's just a condition of electrostatic equilibrium. So if there is no electric field inside this conductor, this terminal and this entire wire must be at the same potential. This is just a conductor. So now I'm touching a conductor to a positive plate. So what's going to happen is that this charge is going to spread out on this positive. The positive charge spreads out on this wire, and this entire circuit becomes an equipotential volume. And remember that all of this charge is on the outer periphery of this wire. This is necessitated by Gauss's law. And the electric field inside has to be zero. Because if there were an electric field, charges would flow. But there is no flow of charge here, there is no current here. Likewise, this entire wire takes up a negative surface charge. E and E is zero. And I'm not talking about what's the electric field inside the battery, because I'm going to talk about batteries in some more detail. So I have a gap here and I've connected these wires, but I have forgotten to make this connection. There is an air gap. Now let me focus on this air gap here and let me zoom in onto this diagram. So initially what I have is that I have positive charge on the gap, and all of this positive charge is on the outer surface by Gauss's law. I have positive charge here and I have negative charge here. Now the electric field inside each of these wires is identically zero because no current is flowing. Now if I were to draw the electric field in a way, in the following way, let's draw the electric field in the following way. I have these positive charges on the gap, so this is the gap, and these are all other charges inside the circuit. And remember, where are these charges coming from? Are they flowing from the battery? No. Charges are available everywhere because there are mobile electrons everywhere. So there is a sea of electrons here, there is a sea of electrons that floods this entire wire. So charges do not have to travel all the way from the battery to this end. They are locally available, they are available here, they are readily available here. And if an electric field exists, these charges will move to the outer surface until the electric field ceases and until the electric field drops back to zero. So the mobile sea of electrons are present everywhere and they can respond to local electric fields. So the mobile sea of electrons will expand in a way towards the outer periphery of this wire so that there is a net excess of negative charge on the outer periphery of the wire. And these electrons that are sloshing out from the wire are locally available. They don't have to travel all the way from the battery. So the slow speed of the sea of electrons doesn't really matter because electrons are available everywhere. So if electricity comes to our light bulbs and it illuminates light bulb, the electrons are not traveling all the way from Mangla or Tarbela. The electrons are available in the wire, and whenever there is an electric field that the electron sees locally, it's going to respond to it. And electric fields travel at the speed of light. We've already discussed the concept of retardation. Now what's going to happen here is that this gap is open. Let me draw the electric field due to these positive charges on the gap. And I ignored these charges for the time being. So the electric field due to this gap at different points is going to point in directions like this. Right? So the electric field here is going to point in this direction because of these gap charges. The electric field here is going to point like this because of these gap charges. So here in white I am drawing the electric field due to the charges on the gap. Right? These charges. Likewise, there exists an electric field due to the gap charges inside this wire as well. And those electric fields lines are going to point in this general direction. Agreed? But the electric field inside this wire has to be zero. And the electric field inside this wire has to be zero. But these are the electric fields drawn due to the gap. Please try to come in time. It's very disturbing. Not only for myself but for the rest of the class as well. So if you would like the electric field inside to be zero, and these are the electric field lines due to the gap charges, there has to be some other field that is set up inside the wire because of all other charges, because of these charges and all other charges in the circuit. So if the electric field due to the gap is like this, the electric field due to all other charges is going to be like this. It's going to be opposite and equal in magnitude to this electric field. The electric field due to all other charges is going to be like this. The electric field here is going to be like this. The electric field here is going to be like this. The electric field here is going to be like this. ये बात समझ आई? क्यों नहीं आई? Let me redraw this. अब दोबारा समझाने की कोशिश करता हूँ. ये बात बहुत अहम है समझने के लिए. field inside the conductors, the net electric field at all points inside the conductor, 0. Now I'm going, any zero electric field, I can make many vectors such that the resultant is 0. Now what I'm trying to do, I'm trying to break up the contribution from the charges inside the gap and all other charges. Now just due to the charges inside the gap, the electric field points like this. At 3 different locations I'm drawing the electric field. Here the electric field due to this line of charges is pointing in this direction. Here the electric field due to this gap of charges is pointing in this direction. ये समझ आ गई बात? Likewise, I can draw the electric fields in this wire just due to the gap charges. But the electric field has to be 0. So in addition to these electric fields due to the gap charges, there are electric fields set up by all other charges. For example, all the charges that have been built up on the lateral surfaces of this wire. Now I'm going to draw those electric fields by yellow lines. So I have an electric field due to the gap charges and an electric field due to all other charges. And these electric field lines have to be equal and opposite to these electric field lines, because I would like the electric field at each point to be 0. So, and why am I doing this? It's going to become clear in a minute. So I have an electric field here, I have an electric field here, I have an electric field here, and a field here. I'm just drawing 3 representative points. Otherwise there are electric fields everywhere. So if I take the resultant of these fields, it's going to be 0. The resultant of these fields is 0. So everywhere inside these wires, the electric field lines are non-existent. The electric field is really 0. Okay. Now why am I doing this? Because I would like to do something really interesting here. Let me draw the same figure over here. Now what I'm going to do, I'm going to close the gap. So at some instance of time t equals 0, I close this gap. So I stitch these wires together. All of a sudden at time 0, I do it instantaneously. So that in the circuital sense, my circuit is now complete. It's a closed circuit in the circuital sense. Now let's look at what's going to happen to the charges. Intuitively, you know that current should start flowing. And when current starts flowing, an electric field must be set up inside this wire. Initially, the electric field inside the wire at time less than or equal to 0 is 0. Because the electric field due to the gap is equal and opposite to the electric field due to all other charges, and the net electric field at each point inside the wire is 0. Now I close the gap instantaneously. Now what's going to happen to the charges at the gap? If I close this wire, what's going to happen to those charges that exist on the gap? जी क्या होगा इन चार्जेस को? क्या होगा जब ये बंद कर दूंगा? These net charges will vanish because you have a depletion of mobile electrons, you have an excess of mobile electrons, and when this gap is stitched together, the net charge just vanishes. So the gap charges just disappear. Okay? So this interface becomes neutral. There are no gap charges on this interface because there is no gap. The charges have relinquished one another. Now this disappearance of charge changes the configuration of charges, so the electric field due to the gap vanishes. Okay, the electric field due to the gap just vanishes. And how long does it take? After time t equals 0, it just takes a time that is proportional to the distance of these points from the gap divided by the speed of light. Alright? And this is instantaneous. So instantaneously, these white electric field lines, they just collapse, they just vanish. Nothing is going to happen to these charges for the time being. These charges still exist on the outer periphery of the wire. But what we have seen is that in the vicinity of the gap, just close to the gap, the electric field lines due to the gap just disappear, and we're only left with the electric field lines due to all other charges. So at this point, the net electric field is now pointing in this direction, Here it's pointing in this direction, here it's pointing in this direction. At this point, the electric field points like this, here it points like this, and here it points like this. So this is what happens in the immediate vicinity of the gap that has now been closed. The electric field lines, due to the gap charges, has just vanished. But nothing is going to happen to these all other electric field lines due to all other charges, because all other charges have not seen the effect of the closure of the gap as yet. The information of the closure of the gap has not yet transmitted to all other charges, because it takes a finite amount of time, albeit a very small amount of time. Now these electric fields exist. Now there has been created in the vicinity of the gap local electric fields inside the conductor. Correct? Now what happens is that there are electrons everywhere. There is a mobile sea of electrons. So there is an electric field that the electrons sees here. And under the action of this electric field, the mobile electrons are going to attain a drift velocity. We will move very slowly with a speed of few millimeters per second. Please don't talk. If you're late to the class, that doesn't mean you have the liberty to just disturb me. So these mobile electrons move under the influence of these electric fields that are now uncancelled, that are the remnant electric fields, remaining electric fields. So a mobile electron here can move under the action of this electric field with a drift velocity which is really small, but it doesn't matter because there are electrons everywhere. It doesn't have to cover a very long distance. So the electron will move in opposite to the direction of the electric field. Here the electrons will move like this, here the electrons are going to move like this, here they're going to move like this, here they are going to move like this, and here they are going to move like this. So in orange, I'm actually showing the drift velocity of the electrons at the different locations. Now what's going to happen is when these electrons, the mobile electrons, are going to move towards the outer surface, there's a depletion of electrons here, so it's positively charged. But when the electrons reach the outer surface, what's going to happen to this charge? It's going to get smaller. The positive charge is going to get dilute. And here, the mobile electrons are moving away from the surface. They're moving inwards. So this negative charge is going to get dilute. So in the immediate vicinity of the gap, what's going to happen to these charges is that they're going to get dilute. Here there is a uniform distribution of charges. Everywhere there is a uniform surface charge density. It has to be a uniform surface charge density. There can be a few minute excess charges at the bends, but these charges are really small. But there is a uniform charge density everywhere because it's a nice uniform cross-sectional homogeneous wire. So the uniform cross charge density exists. But here, at the instance that this gap is closed, electric field lines are set up which create the motion of mobile sea of electrons so that the charges in the immediate vicinity of the gap get diluted. Because now electrons are moving towards the outer walls. So when an electron reaches here, it's going to make this positive less positive. And when electrons are going to move away from these surfaces, the negative charges are going to become less negative. So these negative charges are going to get diluted. So what's going to happen then is that at some instance after this gap has been closed, so at some instance afterwards, t equals 0 plus, okay, some instance afterwards, this positive charge gets dilute. This negative charge gets dilute, and further away from the gap, the charge distribution on the surface still remains uniform. But now there is a positive charge here and a negative charge here on the surface. So the electric field now exists from the positive side of the conductor to the negative side. So there is a net electric field that's going to point in this direction. Now what this electric field is going to do is going to make the charges. So there's an electric field here, there's an electric field here, there's an electric field here, an electric field like this, and an electric field like this, and you move further away from the gap. Now this spreading of the electric field is happening at an instantaneously high lightning speed. it's happening at the speed of light, because the information that the gap has now been closed is traveling or transmitting outwards at the speed of light. So new electric field lines are propagating. And when the electric field lines are propagating, there's going to be a drift velocity for the electrons, because whenever there is an electric field, there has to be a drift velocity of the electrons, and the constant of proportionality is just the mobility. So the electrons are now going to move towards the outer periphery, and they're going to move away from the outer periphery. So now this region is going to get diluted, and then this region is going to get diluted. So the effect of dilution of the charge is going to spread all the way outwards like an earthquake or like a tremor, which is traveling at really high speeds at the speed of light, because the electric field information is traveling at the speed of light. It's going to spread outwards, and this charge distribution gets diluted and diluted. So now this is the process of feedback that is happening. Once the gap has been closed, the information that the gap has closed is going to travel at really high speeds. And the information really means that the electric field is going to readjust at all of these points. And the electric field readjustment causes electrons that are locally available at each of these points to respond. And they respond in such a way that the charge gets diluted and diluted. And the effect of dilution diminishes. Here the dilution is large, but then the dilution becomes less prominent. So at the end, in a few nanoseconds, remember the speed of light is 3 to 10 power 8 meters per second, which effectively means 30 feet in a nanosecond. And if your wire is 1 feet long, it's going to take place, this information is going to spread out in 1/30th of a nanosecond, in a few hundreds of a picosecond. So eventually what's going to happen is that we're going to have a charge distribution throughout this circuit, and let me show you what that charge distribution is going to look like. Now this is a really profound concept that is not generally found in common textbooks. So there's a positively charged terminal of the battery here, and a negative charge terminal of the battery here. And there's some distribution of charges, and this distribution becomes diluted. So these plus signs just represent a logical representation of the density of charges on the surface. So here the density of charges on the surface is large, here it's slightly diluted, here it's slightly diluted. So this effect of dilution has now spread out in the entire wire, and it's spread out at the speed of light. So the electric field reestablishes itself at each of these points, and the information travels outwards. And there are mobile electrons that are located everywhere that can readjust so that this dilution of charges takes place. Likewise, on this other side, there is going to be a distribution of charges and the gradient of charge densities. So the relative number of the positive and negative signs is just a schematic representation of the concentration of charges on the different areas. Here the concentration is largest, the surface charge density is largest. Now what this distribution of charges, when this distribution of charges has been created, what's really going to happen is that an electric field is going to be set up inside this wire. Because here you have a surface charge which is positive and a surface charge that is negative. If I make up a close-up diagram of the wire that exists here, you have a wire. First of all, remember that all of these charges have to be on the outer periphery of the wire. They cannot be inside the wire. Why? Because if I were to draw a Gaussian surface inside the wire, and if I want this electric field to be the same as this electric field, which I really want because I want the flow of current to be steady, and that's only possible when the drift velocity here is the same as this drift velocity, which means that this electric field has to be the same as this electric field, which means that this Gaussian surface must not enclose any charge. So all the charge must exist on the outer surface. So all of this charge that has redistributed itself exists on the outer periphery of this conductor. Remember that. Now if I look at the close-up of this section, what's really happening is that I have an outer shell. Just on the outer periphery I have a distribution of positive charges. And nearby I have a distribution of negative charges. Now I know that this distribution will create an electric field. That electric field is going to point in this direction, E. And that electric field exists inside the wire. Alright? If I have okay, suppose I had this configuration. I have positive charge on the surface, and then I have positive charge here again. And the density of these charges on the surface is still the same. Will there be an electric field inside the wire? No. In order for an electric field to exist, I must have a difference in potential. And a difference in potential exists only when the surface charge densities are different. So this will produce no electric field. Likewise, if I have a scenario in which the cylindrical conductor has a distribution of charges like this, still it is going to produce an electric field, because there's a difference in potential between these sections, and the electric field is still going to point in this direction. So all of this charge is distributed on the surface of the wires in such a way that the electric field inside the wire is constant, and it's parallel to the axis of the wire. Now a uniform electric field has been set up by the transmission of information of the closure of this gap throughout the circuit. The electron C has responded locally to the new electric field that has been set up, and it has responded in such a way so that this gradient of charges is created, and that has produced in effect a constant electric field throughout the circuit. Now when this constant electric field exists, there's going to be drift velocity for the electron. Now the electrons are negatively charged particles, so the electrons are going to drift, which means the C is going to drift in the opposite direction. So this is how current is flowing through the circuit. Initially, the gap is closed, transients are set up, everywhere mobile electrons are going to make their way towards the surface of the conductor, and charges are going to be depleted or they're going to be amplified on the surface in such a way that we get a distribution of charges, a gradient of charges on the surface that produces an electric field in effect throughout this circuit that creates the drift of electron C throughout the circuit, which constitutes the current. So the electric field has been set up. Now I give you half a minute just to think over this, and then we'll move on with more examples. Again, it's a concept of feedback that is at work.